Yes.
Okay, thank you so much for your patience, and my apologies. This is not how I expect this will be happening. Yeah, so we just talked about the TD learning, and this is for policy evaluation. And now we're going to look at how we can actually find the optimal policy. And this Q-learning algorithms is obviously one of the most well understood algorithm and widely used reinforcement learning algorithm. And we're going to start with the standard Q-learning algorithm. And this is very similar to TD learning algorithm, except here because we're considering this Bellman optimality operator, right? So here we are going to have this max over all this action in the when computing the temporal difference. So this is the update for the standard Q-learning. And if you have a linear function approximation, right? If your Q is represented by a basis vector times your parameter theta, you can update theta similarly as before, right? There is your temporal difference term here times the feature basis vector phi there in front of it. And the only difference here is that we're replacing this value functions by this state action value functions, and we're using this max operator at every iteration to find the best action corresponding to the current Q functions. And there are indeed also many other Q-learning variants, like the deep Q-learning is where you use instead linear function approximation, use deep neural networks. And there's also double Q-learning, which uses idea of target networks, and we will discuss in a bit. And then there are also a lot of accelerations of Q-learning algorithms using momentum type of ideas, like the speedy Q-learning and zap Q-learning. So particularly this double Q-learning is kind of one of the building blocks of modern deep reinforcement learning. And the main idea of this double Q-learning and the motivation, I should really say that, as some of you also pointed out about this max operator. So the presence of this max operator actually causes the so-called overestimation bias or maximization bias. The idea is as follows, right? If you look at this estimator here, this is oftentimes a noisy estimator of your true value functions. Hence, you are really using the maximum of a bunch of estimators to estimate the expectation of the actual maximal value. So this will cause a positive bias in terms of estimation. And think about the case where your true value function is actually 0, your reward is 0. This will this estimator oftentimes can be very noisy, so it could be both positive and negative. And when you take the maximum, it will always kind of in favors of those actions that gives you positive and a noisy estimate. So in order to deal with this maximization bias, the idea of double Q-learning is really to introduce another set of estimator for Q. So it keeps track of two estimators of these Q value functions. One estimator used to select what is the best action. And then you use a second Q estimator to evaluate what is the value function at this best action, right? So you see that here this best action is selected based on this estimator at this WA. And then it is evaluated based on another network or another Q estimate, QB here. So this is kind of the double Q-learning algorithm. Particularly at every iteration, you will just flip a coin and randomly update either the first estimator or the second estimator. So the computation cost is the same as Q-learning algorithm, but the memory cost is twice large as the standard Q-learning algorithm. So to give you a better idea of this maximization bias, you can look at this like Sutton and Bartels example. And in this example, say for instance, there are only 4 states. There's And if you look at the state A, there are two actions, right? Either you move to the right or you move to the left. If you move to the right, you will end up in a termination state and you will get a 0 reward. If you move to the left, you also get an immediate reward, which is 0. But you might, in expectation, it will go to other states with expected negative reward. So as you can see in this case, actually the optimal action at state A is going to be to turn to the right instead of the left, because in the left, you always expect some negative reward in expectation. However, when you run Q-learning algorithms, because of this maximization bias, it will often appear that making a left will have a positive value, right? Because this is a random reward, the random reward could be positive. So initially, when you run Q-learning algorithms, it will actually it will strongly favors the left action, which is not optimal, right? On the right figure, you can see that at the very beginning, actually, there is a very high probability that you will actually choose the left action. And if you apply double Q-learning, it actually fixes this issue, and it will be less in favor of this left action, right? So this is the so-called maximization bias. So another issue with Q-learning, other than the maximization bias, is that oftentimes if you were to use function approximation, and if your data are connected from some behavior policies, then in fact, this could lead to divergence, right? So this, again, there are actually many examples that was provided in different textbooks. This is an example that was given by Bert. And this is a particular example where you have, say, 7 states and only 2 actions. And here we're using 8 parameters to estimate your value function. So as you can see, the number of parameters is much larger than the number of states you have. So this could actually fully represent your true value function. If you apply this Wtd learning algorithm, for instance, here, based on some data that are connected from a behavior policy, so this is so there are only 2 actions here in this example. So the solid line is 1 action and the dashed line is another action, right? So in this example, actually, you can easily show that off-policy Wtd learning algorithm actually will diverge. So those W's, which are the parameters you try to learn, will diverge. And this is not only true for Wtd learning, but also true for Q-learning as well. And this was essentially the so-called Deadly Triad that was a concept coined by Richard Sutton in 2018. Which says that if you try to combine both function approximation, even just linear function approximation, with bootstrapping, with off-policy data, it will not guarantee convergence of your algorithm, right? But in practice, we know that you have to use function approximation for large state space, and you have to use bootstrapping for efficiency. And you do only have observations from off-policy data, then what can we do, right? This feels like a bottleneck here. And for this part of actually the first part, which I'm significantly delayed, that we're trying to really to understand what are the asymptotics and non-asymptotics behaviors of these reinforcement learning algorithms. And can we say anything about if we are to using function approximation, how large or how flexible our function approximation should be in order to guarantee convergence? And how we can actually derive what are the sample complexity you need for them to converge. And there are indeed many proofs and analyses for these classical reinforcement learning algorithms. And I think a common recipe here is either to resort to stochastic approximation or the continuous time dynamic systems of the underlying ODEs. So here and you can use all of these to derive the asymptotic convergence or finite time convergence, or even derive very tight error bounds on the convergence. So here I just listed a couple of references. They are by no means exhaustive, right? There are many also recent theoretical developments and many different variations of Q-learning algorithms and TD learning algorithms. And here the orange ones basically highlights those use this continuous time dynamic system perspective, and the the blue references are those that use these stochastic approximation arguments. And later in this talk, I'm going to give you some examples, actually very recent result that that uses either of these approach, and so that you can have a better flavor. What are the technicality of different proof techniques? So I wanted to start by saying that using this continuous time dynamic system has both advantages and disadvantages. The apparent advantages that first of all, I think because they're first of all, it offers a very systematic and also oftentimes unified analysis for different reinforcement learning algorithms. And as you will see later on also. And there are lots of very rich control theory and tools that we can leverage directly. And so you don't really need to have a lot of new analysis. And also another, I think, a key importance of this is that you don't really need to have a clear objective or gradient to work with, right? You just directly work with dynamics and you'll be able to get a full characterization of how it should behave. The challenge, though, is that oftentimes we have to deal with nonlinear systems, for instance, especially even for just a tabular Q-learning setting, because of this max operator, the underlying system is indeed nonlinear, and there are not that many theory about convergence of nonlinear systems, unfortunately, and then it's also very hard to extend it to nonlinear function approximation in many cases. And now let's just see how we can actually leverage a unified ODE analysis and to derive the convergence analysis for a wide spectrum of reinforcement learning algorithms based on existing control theory. So the ODE method is initially introduced by Bokar and mine in this very seminal work. And although it has more than 20 years of history, still these days I find it quite enlightening. And it's in fact also one of the 20 most read articles in SIAM Journal of Control and Optimization. And many of you probably is familiar with the main idea of this ODE approach or ODE method. So basically what it says here is that we can analyze the convergence of any stochastic approximation algorithms by simply tracking the associated ODE in the steady state, right? If the underlying ODE is asymptotically stable, then it actually guarantees the convergence of this stochastic approximation algorithm. And by asymptotic stability, we're really saying that the solution or the ODE converges to some equilibrium point for any arbitrary initial condition. So this is kind of the key idea here of the ODE approach. As you can see that let me just give you a simple example. Say, for instance, if h is just a gradient of some function, then your ODE is essentially going to be the gradient flow, right? But here for reinforcement learning, as you can see, most of the algorithms, those h you have in those updates are not necessarily the gradient of some objective. So the analysis is slightly different from gradient descent. So the ODE method so to be more specific, there is this Bokar and Mine theorem that says the following, right? Suppose you're under some regularity condition, say so there was a typo here, which I did not correct. So this should be actually H. So if your operator H, or this mapping H here is globally Lipschitz continuous, and if your step size satisfies is this Robbins-Monroe step size that is square summable but non-summable. Say, for instance, you can choose alpha k to be just of order 1/k, right? And if your noise epsilon here is bounded, that satisfies this condition listed here in this part C here, then you can, and then on top of that, if we can show that this original ODE is asymptotically stable, and the limiting version of this ODE is also asymptotically stable, then this will be enough to guarantee that there exists a unique globally asymptotic stable. Then this will be enough to show that this discrete time stochastic approximation algorithm will actually converge to the equilibrium point X star. Right? As you can see, this algorithm is super handy in the sense that if you are able to show the asymptotic stability, then you are able to establish convergence. And I'm going to give you some examples like where you can actually easily establish asymptotic stability. Hence, you will get convergence of reinforcement learning algorithms. So the first example is, for instance, for linear systems. We know that for linear systems, there exists a unique stable equilibrium point if and only if this matrix A is Hurwitz. And by Hurwitz matrix, we mean that all the eigenvalues have strictly negative real parts. And particularly if you think about the Wtd learning algorithms, those are indeed can be casted into a linear system. And this stability argument has been widely used and explored in various different Wtd learning algorithms. Say, for instance, if we look at the Wtd learning with linear function approximation, and you can immediately see that if you look at the associated ODE of this stochastic approximation, this is going to be given by some matrix A, right? This matrix A is the feature matrix phi times D. D is the diagonal matrix of your station distribution of your so this D is basically the diagonal matrix of your initial or your station distribution mu. And then you have this matrix, as we see before, gamma times P minus I times phi. And you can actually easily show that this matrix A is actually Hurwitz, because you can see that this actually, you can show that this intermediate, this middle matrix here, gamma times P minus I, is in fact negative definite. So this part is indeed negative definite. And if this matrix phi, your feature matrix phi is also full rank, then this will mean this A will be also negative definite. Okay. So that's kind of the original results that people tries to use to establish the convergence of Wtd learning. So you can also generalize this analysis to other Wtd learning algorithms. Say, for instance, if we consider the double Wtd learning algorithms that we proposed a few years back. So the idea is similar to the double Q learning, where we maintain two different sets of estimators for your value functions, right? You have this estimator, two different parameters, theta B and theta A, and you're updating them symmetrically. And you're using one of those estimators to evaluate your target update, and other one to just keep an online estimate of your value function. Then you can also write down what is associated ODE, and that will have a slightly different matrix A here. But this matrix A is actually closely related to what you see in the case above. And you can also easily show that this matrix A is actually Hurwitz, and if this feature matrix phi is full rank. And then this immediately implies the convergence of double Wtd learning algorithm. Okay. Of course, linear systems are very kind of optimistic, right? That does not really capture a lot of the real dynamics. So we also have many rich theory about stability of general nonlinear systems. So if this H is just arbitrary, or let's say if it is Lipschitz continuous functions, then there was also lots of existing theory that tries to establish sufficient conditions to ensure global asymptotic stability of this nonlinear system. Here I just list one example of it. And you can see that if you are able to find some Niao function V that satisfies these certain conditions, then indeed this implies asymptotic stability. As you can see, that differs from the linear case. This is just a sufficient condition, not a necessary condition. And although this result is very general, it can be very hard to construct these Niao functions. And oftentimes it's also very hard to check whether these conditions actually are satisfied. Nonetheless, still there are some work that shows that indeed for Q-learning algorithms, you can come up with such Niao functions and use that to establish convergence. And we can see that for general nonlinear systems is not really very useful in some sense, that because this difficulty with constructing the Niao function. But in fact, we can show that for some special nonlinear system with particular structures, the story is much nicer than this. And of particular interest is a class of linear switching systems, which is a very special class of nonlinear system. And that has some similarity with linear systems. So the difference from linear systems is that for linear switching systems, here your matrix A is no longer fixed, right? This matrix A will be switched among a subset of matrices based on some switching signal sigma. And this switching signal can be arbitrary, right? It could be just arbitrary policy, or it could be dependent or controlled by your state. So if it is dependent on your state xt, then we call this state feedback switching signal. And there exist actually a lot of interesting results about the stability of linear switching systems. And particularly here is one nice result that says that that says that the linear system is globally asymptotically stable if and only if you can find some full rank matrix L and a family of negative row dominant matrices A1, AM, such that this following condition is satisfied, okay, for any given matrix from A1 to AM, right? So notice that here, this is indeed a both necessary and sufficient condition to characterize the global asymptotic stability of switching systems. And this result is actually closely related to robust stability of uncertain linear time variant systems. I'm sure many of you know control theory much better than me here. And this is indeed a very useful condition. And now I'm going to show you that indeed for Q-learning algorithms, and actually for a very large family of Q-learning algorithms, they are naturally can be characterized as linear switching systems. So for instance, recall that this is how Q-learning algorithm looks like, right? At every iteration, we're going to update our Q functions based on this temporal difference. And with some simple algebraic simplification, you can easily obtain the following ODE model for this Q-learning algorithm. And that is particularly given by this matrix here, times some other vector, okay? And here I should say that this pi qt is denoted as a greedy policy with respect to the current value function qt. This D again is just the diagonal matrix that corresponds to the state action distribution in the steady state. And this P is the transition probability matrix as before, right? And as this may not be immediate to you, but if you rewrite this, like using the notations I just introduced, right? If you denote xt as just the difference between qt minus q star, and if you denote this matrix here as just this matrix A, as you can see that this switching signal here, sigma, actually depends on your current state qt, right? So this is indeed a state feedback switching policy here. So So as you can see that by nature, right, Q-learning algorithm is in fact just a linear switching system. It's not linear system, it's not the general nonlinear system, but it's actually controlled by some switching signal. And different from what we have seen before, that we do have this additional affine term. So it's not completely switching linear system. This actually has this affine term that makes it a little bit more complicated. And you cannot really just use the existing theories that I just discussed to prove the convergence here, or to prove the asymptotic stability here. So what we've shown is that actually this affine term can be easily avoided if you consider if you relate this system to two much simpler systems, particularly if you just ignore this affine term. Actually, if you just throw away this bilinear term, this will give you this linear switching system, right? Which we know how to prove the asymptotic stability. And for this linear switching system, in fact, you can show that this bilinear term here, this affine term here is indeed always, I think it's always non-negative, right? It's less than or equal to 0. I'm not able to remove it. But you can show that this is actually always less than or equal to 0. Sorry that it's not showing up, but yeah, the reason for that is because this pi star is actually the greedy policy response to Q star, right? So any action you take by any policy pi qt, this will give you a smaller value function. Hence, this term is actually negative than smaller or equal to 0. That basically implies that this linear switching system you come up with is indeed strictly an upper bound of this affine switching system. Okay, so that's why we call it an upper comparison system. You can also show that if you just replace or throw out this affine term, just to replace this policy pi or the switching signal here by just a fixed policy, which is kind of the optimal policy pi star here, then you can show that this will be a linear system right now, right? Because this matrix here is just fixed. And you can easily show that this is indeed gives you a lower bound on the original affine switching system. And that's why we call it a lower comparison system. And all of these can be easily derived in just one ion proof based on the definition of the greedy policy. And as we see earlier, that for linear systems, we know that if you're able to prove that this matrix here is Hurwitz, then this implies asymptotic stability, which is indeed what we already shown for TD learning, because this is almost the same as TD learning. If you look at the upper comparison system, since it's linear switching system, if you're able to show that sufficient and necessary condition holds true, then this is also asymptotic stable. Instead, we can show that this matrix A sigma here. In fact, we can show that this matrix here is indeed by itself a negative row dominant matrix. Hence, you can just construct the full rank matrix as identity, and this will immediately give you that sufficient condition you need for asymptotic stability. Right. So this then brings to the following kind of immediate result, which says, like, for the linear system, we know that is asymptotically stable. For the upper system, we know that it's also asymptotically stable. Now, if we look at this this original system, and we can immediately just apply this so-called vector comparison principle that says, if it is if those functions are if this system is upper bounded and lower bounded by this system from the initial point, then there will be the whole trajectory will then be upper and lower bounded by these two comparison systems. Hence, as t goes to infinity, this original system will also converge to zero, or also give you the converge to the equilibrium point, right? So this is kind of a very immediate result you can see. And basically, so far, what we have established is the asymptotic stability of this associated ODE. And by invoking this ODE analysis, this Volcker and Mines theorem, this implies that if you just use any Robbins-Monroe step size and you apply this Q-learning algorithm, this Q-learning algorithm will be guaranteed to converge almost surely as k goes to infinity. Right? I should mention that there indeed are also many other proofs for Q-learning algorithms. This is by no means the first asymptotic result on Q-learning algorithms. In fact, so there are stochastic approximation-based algorithm, approach analysis for this Q-learning algorithm. There are also finite time analysis for Q-learning algorithms that has been recently developed. All of these other proofs are much more complicated than what I have just shown to you. And in fact, the step size here we choose are very general. As long as it satisfies this Robbins-Monroe condition, it will guarantee convergence. Whereas many of these other proofs, they do need to have very special step size choices. And this analysis can be easily extended to many other Q-learning variants, as you can imagine, right? Because it really boils down to just figuring out what is the associated ODE and do some sanity check to see if the underlying system will be asymptotically stable. So particularly, I'm going to give you this example on, let's say, some target-based Q-learning algorithms. And by target-based Q-learning algorithms, I'm just basically saying that we're going to use, as before, just to keep track of two different estimates of your target values. And then we can update your target values either like as the double Q-learning algorithms, like symmetrically, or we can also update your target values like in a periodic fashion, right? Every 50 iterations, you are going to update your target values, or you can update it in a Polyarc averaging fashion, right? We call this averaging Q-learning or average TD learning algorithms, or periodic TD learning algorithms, right? You can easily come up with all of these different strategies to update your target values. Particularly, let's say if you look at this averaging Q-learning algorithm, where here we're going to use a second estimator QB to estimate or to keep track of these target values, right? And we're going to update this QB based on a Polyarc averaging step, which is basically taking the combination of QA and QB at every iteration, right? That's a very simple algorithm. Instead of double Q-learning, so in double Q-learning, basically you're updating QA and QB in a more symmetric fashion. Here we're just taking the average to update the other estimator. And you can show that this actually is also naturally a switching system, and you can easily also show that this is asymptotic, underlying ODE is asymptotically stable, and you can come up with the convergence easily. Okay, I will not go to the details, but I think you can easily see why that is the case. And similarly, we can also extend this to Q-learning with linear function approximation. And for linear function approximation, the ODE is slightly more complicated than before, but still it's a switching system. So what's different here is that it's no longer easy to directly verify those sufficient conditions for stability. The reason for that is because that we know that even for Q-learning with linear function approximation, as we shown earlier, that this does not always converge, right? If your target, if the data that you connect from the off-policy data is far away from the target policy of the optimal policy, then it actually does not always guarantee convergence. So here we're showing that if you actually use this ODE analysis, and if you look at the upper comparison system, lower comparison systems, you can actually easily, from that theorem will provide for switching systems, you can easily cook up some sufficient and necessary condition for guaranteeing the asymptotic stability. And in fact, this is a condition we have, which looks maybe a little bit abstract here, because it's essentially just coming from the asymptotic stability. And we show that if this sufficient condition holds true, then this will guarantee convergence of Q-learning with linear function approximation. And this condition basically essentially also says that your behavior policy or the data you use should be close enough to the optimal policy. And we should mention that there are also similar conditions that has been established in the literature, like the well-known one is the Mellows condition. And that one is much, and that one is based on this nonlinear system, come up with some Lyapunov functions and construct the sufficient conditions for it. So it's much more conservative than our condition, because our condition is really based on this not only sufficient condition but also necessary condition from the switching systems. So in fact, you can also show that you can also very easily verify that the analysis based on some numerical experiments. And here's just one toy example that you can visualize how the upper system, lower system looks like, and what does the original ODE system looks like. And you can see that those systems are indeed very close to each other. So this basically summarizes kind of the roadmap that how you can actually establish convergence of reinforcement learning algorithms, right? You start with some algorithm, let's say Q-learning algorithms, and you write down what is the underlying ODE system for it in the steady state, and you try to understand what are the asymptotic stability behavior of this underlying ODE system. And if this is asymptotic stable, then that gives you the convergence, asymptotic convergence, right? So this is kind of a simple recipe that does not only apply to Q-learning, but potentially many other stochastic approximation algorithms. So maybe I think this is a good time to pause a bit here and see if there are any questions. I do see there are lots of messages in the chat, and I'm sorry that I didn't monitor it yet.
So no worries about the chat. We tried to help you there. But if there are any students with questions, please go ahead.
Hi, Niao. Could you please go through that portion where you discussed that capital pi symbol? I couldn't understand that.
Okay, so the capital pi one is just to for easy notation. Okay, so it's essentially just to choose the so it's just a I think we're getting there soon. Here. Right. So this is just for easy notation. Actually, you can also, I think you can also write this as so basically P of pi QT. So that is essentially to say that I'm going to just use the greedy policy. The greedy policy to pick the corresponding action, right? So this is just a matrix notation to just make it in a more compact form.
Okay, thank you.
Mm-hmm. Any other questions? Please feel free to unmute yourself, and I do wish that we can keep this as interactive as possible. Okay.
Yeah, I have a question, if I might.
Sure, yeah, please.
So it is not really clear to me how we can go from a discrete time update to a continuous time update, because if you prove stability in for a continuous time dynamical system, it is not guaranteed that the sampling, if it is a sampling of that dynamical system, is also stable. So I don't understand how we make this passage.
So there, as I said, there are kind of so showing the asymptotic stability of the OD is not is of course not the only sufficient thing you need to check, right? and there is definitely a gap between the discrete system and also the continuous system. And so basically, as we see that in this ODE method, there were conditions you need to satisfy. Say, for instance, these errors, this noise term at every step has to be bounded, right? And this step size has to be satisfying this Robbins-Monroe condition here, right? So that basically says if your step size is small enough, right? If your error, the noise is controlled at every iteration, then indeed this ODE, this continuous time system, is very much close to the discrete time system. So that implies a convergence.
I understand. Thanks a lot.
So basically, yeah, I think there are really those requirement on the step size and requirement on that the errors cannot increase too fast, right? So that's a very good point.
Yeah, so I have a question. So first of all, thank you very much for this. This is actually a very interesting idea. So you showed that the iteration, so the learning process can be categorized as an affine system so that you can achieve some convergence. So my question is that, so still here, we prove that the iteration process converge, but does it solve the problem of reaching the global optimality? Or it just showed that it converged to something, but maybe it converged to the local optima point, for example. So I just want to make sure.
Good point. So if you look at what I wrote down here, right? So this is indeed the difference between your estimate and the true value function, Q star. So Q star is optimal value function, right? So if by convergence, I mean this Qt minus Q star will converge to 0 for this problem here. But 0 will be the global, will be the equilibrium point here. So basically, if it converges, then it will converge to 0, meaning that Qt will converge to Q star. So it will converge to the optimal value function.
So it means the global optima, right?
Yes, the global optimal value function, yes.
Okay, interesting. Okay, thank you.
And you should pay attention to here. So far, I'm only looking at tabular settings, right? This is not like nonlinear function approximation yet. So this only applies to tabular setting and also linear function approximation as of now. And for those cases, we know that normally Q-learning actually converges to the true optimal function. And later on in the next session, I will talk about if you have nonlinear function approximation, under what conditions you can show also convergence to the global optimal value function.
Okay, thank you. Thank you very much.
Thank you. Thanks for the question. Okay. So maybe I'll just come to the remark really quick because I do want to be mindful of the time. I think we're supposed to have the break very soon. So I think hopefully this gives you some interesting connections between Q-learning and switching system, and this has not been identified in the literature. So there was, and also I can see that the analysis here is quite intuitive, right? You just basically look at how the system should look like and understand the asymptotic stability of it, and this gives you the convergence instead of some like just some upper bounds or playing with the stochastic approximation directly. And in fact, there was nice things about using this ODE analysis in the sense that you can, as I said, exactly characterize the behavior so that you can get much tighter conditions, much tighter bounds, and much weaker assumptions you need. So there are, of course, many open questions, right? First of all of this only shows asymptotic convergence. And we know Q-learning asymptotic converges and also double Q-learning asymptotic convergence. But which one is better? This does not say anything about like their finite time behavior or which one is faster than the other one, which one is stable than the other one, right? How do we compare different algorithms based on the asymptotics, which I will discuss also very soon. So there is also, as Emilio pointed out, there was a difference between the discrete time dynamics and the continuous time dynamics. Those are not exactly equivalent to each other, right? How do we characterize their differences? And so far we have talked about asymptotics, but this does not really give you a finite time guarantees. Establishing the finite time convergence will then need to resort to the discrete time dynamics, right? And we do have some interesting recent ongoing work that's shown that in fact you can also get much tighter bounds by directly looking at discrete time switching systems instead of the continuous time. And ideally, hopefully, this will inspire the potential to design new algorithms based on this control perspective and how we can leverage some of the robust control theories to design something much more efficient and reliable. So lastly, as I said, in the next, I will also talk about how can this be generalized to not this approach, but how, like if we have nonlinear function approximation, essentially we will have some non-convexity there. When does this guarantee global convergence to the globally optimal value functions? And that I will discuss in the next section. And I'll maybe just pause here and give you guys some time for break, and hopefully we'll see you back in 20 minutes or so. Yeah. Meanwhile, if you have any other questions, feel free to just ask. I will also try to read some of the chat and try to answer the questions here during the break.
I just suddenly have an idea regarding the results. So here, actually, you use some results regarding the stability of continuous time linear switch system to reason about the convergence of the training process. So I believe, I'm not sure, but I believe there is some similar results also for discrete time switch linear system. And would it be possible to use those theory to reason about the convergence? Because the question before me, so he just asked, so this is a theory regarding the stability of continuous time switch, a linear switch system. So it also depends on what is the sampling frequency. So when you discretize it, why don't could we directly use those theory from regarding the discrete time system?
Right, that's a very good question. That's a natural thinking here, right? So ideally, if you wanted to characterize the finite convergence, you will have to use those analyses for discrete time dynamics. So I think the difference here is, first of all, the underlying like the Q-learning algorithms or this original algorithm is stochastic by nature, right? So in principle, those are stochastic discrete time switching systems. And my understanding is there is not much work in terms of understanding the stochastic dynamic systems, unlike the deterministic dynamic systems. Right, I think that's one issue. And for sure,
I was just saying the stability of deterministic discrete time switching system. Yeah. So I think there should be some results. I'm not sure, but I think there should be some result regarding stability of deterministic discrete time.
Exactly, yes. And as said, that would not be sufficient here, right? Because you do have this stochastic noise at every iteration.
Okay,
so,
I see, yeah. So
that's why we kind of use this OD analysis by resorting to the continuous time dynamics and use this OD analysis says if the noise is controlled well enough, the step size is chosen well enough, then this will be close to each other. But I think that's definitely also a viable approach to just directly look at the discrete time dynamics instead of resorting to the ODE.
Then we don't need to think about what should I, so because that's the continuous time stuff and you're reasoning about something which is discrete time and then you still have a gap for it. But now I see the point. Thank you.
Correct. Yeah, that's a very good question. Yeah, thank you.
Actually, second. Okay, we can start now, actually. Yes.
All right. Yes, let's do that. All right, so let's continue the discussion. And as we mentioned earlier, that all of the results are for asymptotics. And how can we compare different algorithms based on their asymptotics, right? So particularly, I'm very interested in, let's say, just comparing, say, for example, Q-learning and the double Q-learning algorithm. And the reason for that is, as we showed earlier, that double Q-learning was proven to be helpful with reducing this maximization bias and was extensively used indeed in practice, especially in many of the deep RL algorithms. This is kind of one of the building blocks. So recall that the Q-learning algorithm, if we were to use a linear function approximation, basically looks like the following. And if we were to use double Q-learning algorithm with linear function approximation, we're going to keep two separate estimators for the value functions. One is using parameter theta A, the other one uses the parameter theta B. Here in particular, I'm adding this coefficient beta k here, and beta k is just a Bernoulli random variable because we're going to update either of those updates based on flipping a coin, right? So at every iteration, we either update A or B. So, and as we mentioned earlier, that the essence here is really to use one estimator for selecting the best action or the greedy policy, and use another estimation to evaluate the value function. So as we shown earlier, that you can show that both algorithms converge asymptotically, but the question is, which one is better then? Like, which one should we use actually, and why does double Q learning actually can potentially lead to faster convergence or better performance? So far we have shown that the asymptotic convergence, which is like almost a sure convergence, but even in the asymptotic regions, we can also talk about distribution convergence, right? And this is actually indeed not only characterize the convergence rate, but also characterize the dependence on the system parameters. So for instance, here we want to, I think a good way to maybe just compare two different algorithms in the asymptotics is based on comparing the asymptotic variances, right? And that basically characterizes how stable each algorithm is. So in order to consider the asymptotic variances, we're going to introduce the notion of asymptotic mean squared error. And this is nothing but just taking the trace of this asymptotic covariance sigma term. Okay, so it's like you take the square norm of your estimator theta k minus the optimal solution theta star. For double Q learning algorithm, because we have two different estimates for the parameters, so we can define the asymptotic mean squared error for both of those estimator parameters, theta A and theta B, right? And we can also consider the asymptotic mean squared error for the average of them, right? The average of them is also a good estimator for the Q value functions. So we have this result. Sorry that I did not put a reference here. And also I just look at the chat. Yeah, thank you guys for providing those references in the chat. So this is a work that we had from last NeurIPS 2020 on the comparing the efficiency of double Q learning and Q learning. It's actually a very simple result, I say. So the result is basically as follows, right? If you compare these two algorithms and let's consider both of them using the same scale of step size 1/k for both Q learning and double Q learning. And we can show that if both algorithms converges asymptotically, because we know that if you use linear function approximation, convergence is not always guaranteed, but suppose there are some certain sufficient conditions like the Mello condition or what we proposed earlier satisfied, then suppose both algorithms converge, then we can show that under very mild conditions of like say basically you need this step size G to be sufficiently large, such that we can show that the asymptotic mean square error of any of your output of your double Q learning estimator actually is strictly worse than the asymptotic mean square error of standard Q-learning. Right, so this C0 is some positive values, G is also the step size, so it's also positive. So this is strictly worse than the asymptotic mean squared error of the standard Q-learning, which actually comes out quite a bit surprise, right? Because if you think about all of this, double Q-learning was really trying to reduce overestimation bias to stabilize the learning process, but it actually ends up to have a larger mean squared error. However, we also shown that if you take the average of your two estimators, theta A and theta B, and you look at the asymptotic mean square error, actually it is actually the same as the asymptotic mean square error of the standard Q-learning. There are a couple of things that we need to pay attention to here. First of all, for the way that for us to make a fair comparison here, we're using the step size of a double Q-learning that we're using is twice as large as the step size of the standard Q-learning algorithm. And the reason for that is because for Q-learning algorithm, double Q-learning algorithms, we're only updating one of those estimates at every iteration, right? So if you choose the step size to be twice as large as the standard Q-learning, then that is a fair comparison in the sense that this will guarantees like similar convergence, at least the same like transient behavior among those two systems with the same convergence rate. And now then it makes sense to compare their covariances and asymptotic mean square error. So as I said, the result here holds true for tabular setting or linear function approximation. We don't have a result for linear function approximation yet. And I will show you kind of how we establish this result is not actually very challenging. But before that, let me just maybe first to show you some kind of numerical studies we had that illustrate what we have proved in the theory. Right, in the theory, we've shown that double Q-learning with twice as large as a step size actually has worse asymptotic variance comparing to Q-learning algorithms. And here is again the Baird example that we discussed earlier, which actually is an example where Q-learning could fail when you use a linear function approximation. And to make Q-learning work, right here, we use like a larger discount factor. So in the original counterexample by Baird, they were using like a discount factor, which is like 0.99. Here we just use a moderate discount factor so that both algorithms will actually converge. And if you look at this figure, this red curve is how the Q-learning algorithm behaves. And this blue line is the double Q-learning algorithm if you use the same step size as Q-learning algorithm. As you can see that if you use the same step size as Q-learning algorithm, double Q-learning will converge much slower than Q-learning algorithm, right? The reason is kind of also straightforward because you are only updating one parameter at a time rather than two of them. However, if you use twice as large as the step size as Q-learning, double Q-learning actually converges in the same rate, right? Initially, as you can see, the transient behavior is nearly the same as Q-learning algorithm. However, asymptotically, you see that the double Q-learning with twice step size has much larger variance than Q-learning algorithm. Right, you can see it here. There's larger asymptotic variance. But if you look at the double Q-learning algorithm with the average estimator, the average estimator actually has the same variance as Q-learning algorithms as we predicted in the theory, which is what you actually observe in all of these experiments. Like in all of these three figures, you see that the one with the variance of the variance of the double Q-learning algorithm actually is the same as the Q-learning algorithm. So this basically perfectly matches what we predicted in the theory for this particular example. But what about another example? Okay, so this is another example about the grid word, which is also a tabular setting, but we're using some linear function approximation to estimate the value functions. And in this example, you see something similar, right? You see something similar that if you use the same step size as Q-learning algorithms, then double Q-learning actually performs worse, has slower convergence. So you have to actually really use the twice the same as the step size. If you use the twice as large as the step size, it behaves very similar at the beginning. And again, here you see that the double Q-learning with the average estimator actually has the smallest, actually has a much better asymptotic mean squared error or asymptotic variance. So you might wonder, like, what happened? Like in all of these examples, it's not really clear that like you don't really see this phenomenon of a maximum bias, right? So let's just look at that example we discussed earlier by Sutton and Bartle about the maximization bias, right? In this example, we shown earlier that in fact there was this maximization bias of Q-learning algorithms initially, but double Q-learning was able to avoid that. And here is again the figure where we consider that both double Q-learning with twice the step size and double Q-learning with the average estimator, right? Both of them actually converges better than Q-learning algorithm. However, if you use much larger, like, so this is the first left figure is in the tabular setting. If you consider the same example, but if you use much larger, if you use like neural network function approximation instead, which is oftentimes what people use in practice, then you will see that there's no overestimation bias phenomenon anymore. Right, so Q-learning algorithm with neural network function approximation does not really have any overestimation maximization bias at the very beginning. But still, in this case, you can see that double Q-learning performs better, slightly better than Q-learning algorithm, and especially in terms of asymptotic mean square error, is much better than the Q-learning algorithm. So this seems to suggest that. Maybe like using nonlinear function approximation makes things different, right? But I think the bottom line here you can see is that the punchline here you can see that is really that if you were to deploy double Q-learning algorithm, then you should be using like at least twice the same step size as Q-learning algorithm to ensure at least the same convergence rate. And then you should be really outputting your average estimator instead of just either one of those estimators you use to estimate your value function, right? So that's kind of some interesting observations from our theory, and which happens to align very well with the numerical implementations. Any questions at this point before I show you kind of how we establish this result?
Please go for it.
Yes, I have a question. So, what about soft Q learning? So, I think that again, what's the comparison of double Q learning with soft Q learning? Where in soft Q learning you try to avoid this maximization bias by using entropy regularization and penalizing deterministic policies at the beginning of the learning process.
Okay, that's a very good question. So first of all, yes, soft Q learning, which kind of smooths out this max operator that also helps with maximization bias, right? So in practice, people use soft Q learning also a lot. Here we did not make any comparison to soft Q learning algorithm. I think that would be very interesting future work to do. And in terms of using entropy regularization and all of these, I think I will also talk about this in the next part. We'll be also discussing more about the role of entropy regularization and softmax learning type of algorithms. Yeah.
Thanks a lot. So by using entropy regularization, so let's say that this is an implicit explanation of why using entropy regularization. There's no rigorous justification. While with WQ learning, we justify rigorously that you deal directly with this maximization bias. Is this correct?
Sorry, I don't hear you very well. Can you repeat your question?
So I'm asking if with WQ learning we justify rigorously that the maximization bias is not anymore an issue. Because with software learning there's no rigorous justification. It is just an intuition behind entropy regularization.
So for double Q learning, the essence here is really that to handle this max operator, you are using a different set of estimates to find, you are separating this, the selection of best action from the evaluation part. But for soft Q learning algorithm, it's different, right? You're really just using a softmax operator. And then there you don't necessarily encounter this maximization bias that severely, I mean, because the max operator is much more non-smooth than the softmax operator. So the softmax operator kind of will not have such a large maximization bias. Right? So the kind of the motivation of those two algorithms are slightly different. Yeah.
Okay, thank you very much.
But that's a very good question. Yeah, I think yeah, it will be interesting to look into the differences between these three algorithms. Yeah.
Thanks.
Okay. All right then. So maybe I will just give you a quick, brief sketch of how we derive this result. Actually, again, as I said, this heavily relies on like existing theory on dynamic systems and control theories. And this is nothing really very new here. So if we consider this general linear stochastic approximation, okay, with this, say, this 1/k step size. And here for simplicity, I'm going to assume that it will converge to some point that is just a 0, so that we just look at this asymptotic, so that we don't need to bother with this Q star here. And suppose we define this matrix A as the matrix associated with underlying ODE in the steady state, and this other covariance matrix of this affine term B as the following. Then there is a very kind of classical result that says that if you select this step size G properly, such that this matrix 1/2 times identity plus G times A is Hurwitz, then the asymptotic covariance of your stochastic approximation algorithm is indeed the unique solution of the following Lyapunov equation. Okay, so you can basically exactly characterize what is the asymptotic covariance matrix is by just plugging in what are this matrix A and what is this matrix sigma B there, right? So, and we can use this result to establish what are the asymptotic covariance of both Q-learning and the double Q-learning algorithm by writing down what are the corresponding Lyapunov equations. Right, if you write it down here, you will see the only difference here is that the matrix A in the steady state is different, right? So this is already something we see before, right? For this matrix A in the steady state for Q-learning algorithm, assuming that your policies, because in the steady state, your policy is already close enough to the true optimal policy. So here A is just this a matrix that was defined based on this optimal policy pi star here that we see before, which is indeed Hurwitz, right? And we can also write down what is the matrix, corresponding matrix A for this double Q-learning algorithm. Again, this is what we have shown before as well, which you can also show in this matrix is Hurwitz. And if you select the step size G properly, then you can show that this matrix here is also Hurwitz matrix. And then now it's the basic observation. You can see that because of this kind of symmetric nature of this matrix A of double Q-learning algorithm, you can actually show that this this asymptotic covariance term should have this special structure, which is also symmetric. Right, and if you look at the kind of the relationship between these two Niao equations, if you add this, if you take the sum of the rows of this matrix A, you see this recovers the A matrix in Q-learning. And since, as we mentioned from before, that this asymptotic covariance matrix is indeed the unique solution to this Niao equation. And these two seems to have two different, and using this, you can actually easily construct a solution that satisfies this other Niao equation as well. So this essentially implies that if you take the summation of V matrix and C, taking half of it, then this will actually should be exactly the same as the asymptotic variance due to the uniqueness of this Niao equation. And this immediately then implies that the asymptotic mean square error of the average estimator should be the same as the asymptotic mean square error of the Q-learning algorithm, because they have the same asymptotic covariance terms. And also by similar reasoning, you can show that indeed the asymptotic mean square error of either of those estimators is strictly worse than that of the Q-learning algorithm, because you can show that the trace of this upper part of the matrix is strictly greater than the trace of this of diagonal matrix part. So that basically completes the proof, right? As you can see, that is really nothing magical here, just to try to characterize what does the asymptotic covariance look like, and you will be able to establish this type of relationship between these two algorithms. And you can do this also potentially for many other Q-learning variations and see which one has the smallest asymptotic covariance. And as I said, this is also gives you some motivation how you can actually design more principled algorithms, right? By trying to see, based on this Niao function equations, trying to design ways to minimize the asymptotic covariances. So this basically summarizes what I want to discuss. There is a little bit delay, so now this is actually the summary for the part one. That we can see that there are many other rich and useful control theory that can help us to build better understanding of the asymptotics of reinforcement learning algorithms. I only focus on asymptotics for this part. In fact, you can also leverage a lot of these theories to establish finite time convergence of reinforcement learning algorithms as well. And I think the interesting part is really that can we leverage this to really design better algorithms with faster convergence, potentially more robust, better stability, which remains a largely open question here. And in the next, we will be moving on more to the nonlinear function approximations. So that will be kind of the part two of this lecture is what can we say about nonlinear function approximation? As we mentioned earlier, right, there is a huge gap between the theory of RL and the RL used in practice. In practice, almost always we're using deep neural networks for estimating the value functions because of the state space is so large. But in most of the theory we see so far that only applies to linear function approximation. And in fact, even for linear function approximation, sometimes it could diverge when you are combining it with off-policy data, right? So there is a huge gap between what people use in theory and what people can prove in theory and what people use in practice. And as I said, there is really no way that you can avoid using nonlinear function approximation, because the state space is so large, and you do have to have enough representation power in order to generalize to other states. right? So the fundamental question we want to ask is like, if we're using nonlinear function approximation, will it converge, and under which conditions should it converge? How much overparameterization do we need in order to guarantee convergence? And how does it generalize to other states and other policies? So in this part, I will focus more on the convergence part. And as we mentioned earlier, that there is this deadly triad issue with reinforcement learning in general, that if you combine function approximation with bootstrapping of policy data, it could lead to divergence, as shown by many examples that we discussed earlier. On the theory side, like people have been using Q-learning with linear neural networks for training, like for like playing like Atari games and many other video games, and showed great success. Like they're able to achieve superhuman level performance, and they're able to learn very good policies. Then what happens here, right? What's going on here? And in fact, in this paper by Van Hasselt in 2018, they listed a couple of hypotheses. So they were saying, like so they were basically hypothesizing that maybe because of these other techniques we were using, that actually eases the divergence issue. So for instance, because we're using very large function approximations, then it actually helps with it actually is less likely to diverge, or because we're using these targeted networks to cure the overestimation bias, or this double Q-learning type of algorithms to reduce the overestimation bias, then this helps with this also helps to ease the divergence. Or maybe it's because we used multi-step returns instead of just one single just looking ahead for one step. Like when you compute the temporal the target update, instead of using just look ahead for one step, you look ahead for multiple steps. This will also help with the divergence, help with avoid divergence. Or because we use experience replay and we're prioritizing the samples and reweighting the samples, and this helps as well. So I think there are a number of hypotheses here, and they were able to, they run many experiments to see like which one actually is helpful. And turns out all of those are somehow helpful, right? If you use target networks versus without target networks, you get much better performance. But they were only able to justify it numerically, and still it remains largely open, like theoretically speaking, like which one of them is the main reason that eases the divergence, right? And in this talk, we're trying to maybe shed some light on the nonlinear function approximation part. Does it mean, is it true that if we use larger and more flexible networks, then it will help with the convergence? Which is in general, intuitively for, this may not necessarily be the case, right? If you think about if you use larger networks, it makes your problem even more non-convex. And then it's more likely that you will be stuck at some stationary points or some saddle points rather than converging to a global optimal solution. So in this next, I will basically just look at more simplified settings, not deep neural networks. We're going to look at just a two-layer neural networks, and we're going to see like whether this will lead to global convergence to the optimal, to the value function, and whether and how many neurons, how large is the network you need in order to guarantee certain convergence. So to start with, I'm going to look at just the TD learning with neural network approximation, right? Again, this is kind of the very basic algorithm for policy evaluation. For given policy pi, you want to evaluate what is the value function V. And for simplicity, I'm going to denote this X as just the feature vectors for a given state S, okay? And this X is going to be a d-dimensional vector, and D is much smaller than the state space. And I'm going to consider the following function approximation for your value function V, which I denote as V hat. And V hat is given by 1 over square root of M times the summation of some coefficients AI times this rectified linear unit. And by this plus sign here, this really refers to I'm taking the max between a given vector U and 0. Right, that's the kind of the standard rectified linear unit or activation function use. And pay attention to here that we use this particular coefficient 1 over square root of M, which terms to be actually very crucial indeed for the analysis. And you'll see why that's true. And for simplicity here, I'm going to assume this coefficient A are fixed. And those are randomly generated from this Radmacher distribution, like from -1 and 1. Okay, and I'm going to also initialize them in a symmetrical manner that the first M over 2 coefficients will be the negative of the last M over 2 entries of A. Okay, and I'm going to also initialize those weight matrices W to be just the IID Gaussians also in this symmetric manner. And for now, since A are fixed, so the only parameter are those weight matrices W, right? And for TD learning algorithm, we're going to just update our parameter W. And the TD learning algorithm here, I call it neural TD learning algorithm, which basically performs the following, right? Like what we see before. So at every iteration, you update your weight matrices W by adding this step size alpha times the temporal difference, right, evaluated, and times the gradient at W, right? If you look at the gradient of W here, we'll have a form for that, right, later on. So why is this so one thing you might be wondering, like, why does the TD learning look like this in the functional approximation setting, right? Why do you have this extra gradient term here? So in fact, I think TD learning algorithm was oftentimes compared or can be viewed as solving this minimization of mean square Bellman error, right? Remember that for any value function, it actually satisfies this Bellman equation. And in order to solve this, you can basically just say, let's just minimize the mean squared Bellman error, right? So the optimal solution or the minimizer of this problem will be essentially going to be the value function, right? Because the value function will be driving this objective to be 0. And here we're going to just represent our value function as this parameterized function we had. And if you write down kind of the gradient of this objective, you will see that the gradient looks very similar to the TD learning algorithm that you use, but it's slightly different, right? In fact, the TD learning can be viewed as a stochastic semi-gradient, because like if you write down the gradient here, you will see that it will have this temporal difference term, right? Delta, which is this whole thing here. So my pen is not really working well. But you can also see that if you take the gradient, so you will have this temporal difference term here, and you also have the gradient of this first term, right? We had, and you also take the gradient of this second term, which involves this conditional expectation, right? And this other term. But for TD learning algorithm, we're just showing away the gradient of this second part completely. We just use the gradient of this first part, right? So it's not really the true gradient of this objective. That's why we call it a semi-gradient. Okay. So if you use a neural network approximation, then this objective immediately becomes non-convex. If you use linear function approximation, this is still a convex function, right? Because it's a quadratic function inside of it is linear. So it's convex in the linear function approximation, but it's immediately non-convex if you use neural network approximation. And you should also pay attention to that there is an approximation error between the function, the parameterized function we had to use and the true value function, right? The true value function is not necessarily represented by this two-layer neural network. So as you can see, this is very different from like the gradient descent, right? In like, and it's very kind of unintuitive why applying neural Wtd learning algorithm might lead to global convergence, right? Because first of all, it's not really the gradient. Secondly, this is a heavily non-convex problem. Lastly, there is a certain approximation error, right? So can we show that this neural Wtd learning converges to the true value function V? And if so, how many number of samples or how many number of iterations do we need in order to converge to an epsilon optimal solution? And how many neurons or how large is the network should be in order to get an epsilon optimal solution, right? That's all the questions we're interested to figure out. So indeed, there are lots of theory in the literature about Wtd learning algorithm with linear function approximation, right? And they're able to characterize how many number of samples or iterations do we need to convert to the true value function within this linear function class, right? There were some recent results for Wtd learning with projections, Wtd learning without projections, IID settings, and those are kind of the recent breakthroughs in the theory side of Wtd learning algorithm. But here we're dealing with nonlinear function approximation, particularly this two-layer neural network type of function approximation. So there are also a very active line of research in deep learning theory that studies the generalization of gradient descent type of algorithms with this two-layer overparameterized neural network. And they're kind of, and these are kind of also in the spotlight of deep learning theory that shows that if the number of neurons, let's say the M, you use the network width is infinity. If this goes to infinity, then you can show that this essentially mimics to a reproducing Hilbert kernel Hilbert space. And then you can actually show global convergence. And this was proven in Jacot and Chizat paper. But of course, in practice, nobody uses infinite number of neurons, right? We oftentimes just use finite number of neurons. So there were results shows that if you use like a polynomial, if the number of neurons you use is polynomial in terms of number of samples you have, then you can show that actually it also, if you just apply gradient descent, you will converge to the optimal solution, or oftentimes it gives you zero training loss. But and there were also some results for stochastic gradient descent. Let's say for classification problems, people can show significantly reduced overparameterization complexity. Instead of a polynomial dependence on the sample size, they only get polylogarithmic dependence on the number of training samples you have. So those are kind of the recent advances in deep learning theory. And it'd be interesting to see how this can be generalized to understanding Wtd learning or the Wtd learning dynamics, which is significantly different from gradient descent dynamics in several aspects. First of all, right, unlike the gradient descent or supervised learning regression settings, where basically your observations are just you have the labels and you do have you have the kind of, you have the input, and you have directly given the labels, right, noisy labels. Whereas here in the reinforcement learning setting, we are not directly given what are the estimations of your value functions. We will only be given just rewards, right? So those are very different from the gradient descent or from, say, regression settings. And secondly, in many of these regression classification problems, people were able to show that, in fact, if you initialize your neural network as what we discussed earlier, and if your number of samples m is sufficiently, number of network size is sufficiently large, then you can show that your estimator does not drift too far away from your initial weight W. So this is also so-called the lazy training regime, where basically your parameter is close enough to the initial W0. So more or less, your function approximation is like linear function approximation, essentially. So all of these existing result requires that your network size to be polynomial in terms of the number of samples. And in the TD learning setting, this basically implies you need the polynomial dependence on the state space, but the state space is so large, right, in general. And if your overpolarization is larger than the state space, then this is no better than just applying the tabular TD learning algorithm. You don't really, there's no benefit of using function approximation. So the question we are interested in to see is like, is this really necessary, right? Can we have modest overparameterization that is independent of the state space? And can we actually control this drift among of these network parameters? So before that, maybe I will just give you a kind of a quick motivation of what is this so-called neural tangent kernel that was extensively studied in recent years in deep learning theory. So if you look at this value function, which is represented by this two-layer neural network, you can actually use, say, by first order Taylor expansion, right? You can rewrite, let's say it's approximately equal to, let's say you just do the Taylor expansion around your initial weight W0, right? So this is your function value at the W0, and then you can compute what is the gradient, right? The gradient of this will be just because this is the maximum between 0 and this linear function. So the gradient will be the indicator function, right? If your W transpose X is positive, then it's 1. If it is less than 0, then it's 0, right? Remember that the rectified linear unit, how does it look like? And times X, that is the gradient of at W0, and you have this W minus W0 in the first order term. And you can see that because of this definition of this rectified linear unit, actually this term is the same as this term times Wi, right? Because so basically, you can easily see that by definition, that V hat is just your gradient times Wi0, okay? So basically, this simplifies it to just this linear term, okay? So your value function can be approximated by this indicator function evaluated as the initial weight matrix W times this X, your feature vector, times Wi, right? So this is more or less like a linear function approximation. And the idea is that if W0 is close enough to W, then your value function will be approximately linear at every iteration, right? Approximately linear. And if your number of samples, or number of network neurons, M goes to infinity, then this will actually reduces to the so-called neural tangent kernel, right? You can define the neural tangent kernel as just taking this, so this will be, first of all, because W0 are random Gaussian vectors, right? If your net M goes to infinity, so these are just random features. If your net M goes to infinity, this is then associated with this neural tangent kernel in the infinite with limit regime. where you're just going to take your feature, your random feature vector is going to the indicator times x, right? You take the inner product between them, taking the expectation over W0. W0 is just the IID Gaussian random vector. And this is a neural tangent kernel is well known to be a universal kernel in the sense that actually it can represent, it's actually the corresponding reproducing kernel Hilbert space is indeed dense in any continuous function space. Meaning that if you have any continuous function with a compact domain, then you can find, you can approximate it arbitrarily well using this kernel function here. Okay, so that is kind of more or less the essence here of why we use this type of initialization, and in fact also for neural tangent kernel, this may look a little bit complicated, but you can actually exactly have the closed form kernel computed, which is given by some arc cosine functions. So one of the key assumptions we make here is that we're going to assume your value function v is going to reside in this reproducing kernel Hilbert space generated by this neural tangent kernel. As I said, this is a universal kernel, meaning that basically any continuous function, as long as your value function is continuous, it can be well approximated, right? So v is should be belonging to such reproducing kernel Hilbert space. In particular, on top of that, we are going to assume that the norm, like so this small v is basically the representation of your value function in this kernel space, and we're assuming that your representation with those coefficients are bounded in L2 norm. Okay, so which is kind of just a bounded assumption here. You don't want those norms to go to infinity, and this essentially basically characterize how smooth your value function is, right? If your value function is really smooth, then you would expect that this v bar is smaller, right? So this is corresponding to kind of the RKHS norms in this space. So here comes our main result. Our main result basically says the following. We have two set of regularization here. So the first result says if we're going to enforce a max norm regularization by projecting our weight matrix W into this set, which says that basically we're enforcing the Wi to be close enough to the initial point within some distance that is proportional to the number of neurons you use. Then we can show that the total number of neurons, if you just set it to be of order 1 over epsilon square, and you set your step size to be of order epsilon square, then you can show with high probability that your value function that you estimate your output, this is actually the average of the output, is going to converge or is very close to the true value function with this type of error bound that depends just in the order of 1 over square root of t. Right. So that being said, you only need a very modest overparameterization in the order of 1 over epsilon square, and then you will be able to actually achieve global convergence here for this neural TD learning algorithm. But the kind of the cost you need to pay is that at every iteration you need to perform this projection. But performing this projection is actually relatively easy because this is a max norm regularization, right? So you're basically, you can do this in parallel. And this max norm regularization is widely used actually in deep learning. Like particularly, this is also closely related to dropout and many other things people used to train neural networks. So the other result we have is that if we assume, if we don't do any regularization, if we don't enforce your weight matrix to be within the proximity of W0, your initial point, then we've shown that we can still get global convergence to the true value function as long as you stop early, in the sense that if you just stop your algorithm for a fixed number of iterations t, That's roughly in the order of 1 over epsilon square times alpha. If you just run this many number of iterations, not too more than this, but just this order of iterations, and with the properly choosing step size and the number of networks, neurons you need is of order t. So basically this is kind of saying that you need slightly more neurons than the number of iterations you need, right? So this is also in the so you need to have more overparameterization. So you need to have some overparameterization here, essentially, right? The number of neurons you need has to be more than the number of samples you have seen. And then under these conditions, you can also show this type of convergence. And maybe let me just discuss this a little bit more so that you have a better picture of what's going on before we dive into the kind of the technical details. So the kind of the highlight here is basically says that you need some sort of regularization, right? So either through this max norm regularization or through this early stopping. So early stopping is also widely used regularization technique for training neural networks that people observe in practice, especially like in training games or many adversarial machine learning problems where you have noise in your labels. Then they've shown that using early stopping actually helps you to generalize better, right? This is kind of in our theory, we've shown that this is also true for TD learning or for reinforcement learning. So you need some sort of regularization in order to generalize or in order to converge to the optimal solution. And by adding this regularization, then you only need a very modest overparameterization, okay? And as we said, in the max norm regularization case, we only need the 1 over epsilon square number of neurons. And this is much better than the existing result that was provided in this paper here, these two papers. They've shown that if you do L2 regularization instead of max norm regularization, you actually need much more neurons. They've shown that you need 1 over epsilon 8 number of neurons if you apply this L2 norm regularization. And know that L2 regularization is much more harder to compute than the max norm regularization, right? Because the number of neurons is so large, and the L2 norm regularization, you cannot really do it in parallel as the max norm regularization. So this is much more kind of computationally efficient than the other one as well. And without the explicit regularization, we've shown that, so basically we needed to have smaller step sizes in order to make sure that your W does not drift too far away from your initial point. Hence, that increases slightly the sample complexity. And in this case, if you just don't use any sort of regularization or projection, the overparameterization complexity we derive is 1 over epsilon 6 instead of 1 over epsilon 2. So you pay a little bit more price there without doing any projection or regularization. And the sample complexity is also slightly higher, okay, than the case where you apply max norm regularization. But the trade-off is that with max norm regularization, you were kind of you were restricting also the network representation power, right? Because you are restricting the weight matrices to be bounded somehow. So there is a trade-off, right, between the sample complexity, overparameterization complexity versus the representation power of your neural networks. And lastly, I think we should mention that the overparameterization complexity, as you see so far, only depends on sort of this 1 over epsilon, the accuracy that your target error, and the this parameter V bar, which kind of measures how smooth your value function is and the bounds of your value function, the true value function, right? This has nothing to do with the size of your state space. So unlike this other work that I should mention that uses the uses neural networks, and they've shown that you need polynomial in size of your, so this should be state space S. You need a polynomial in the size of state space, number of neurons, in order to convert to the true optimal solution, which is apparently impractical when your state space is very large. So that kind of is kind of the main message I want to discuss about this neural tangent like the neural Wtd learning algorithm. And with the remaining time, I want to maybe also discuss very briefly the proof. And the proof, you look at this result, you think it is so sophisticated, but the proof actually is fairly straightforward. And also this gives you another flavor of kind of how to derive finite time analysis based on this discrete time stochastic approximation scheme. So this is a very different flavor comparing to the ODE analysis we discussed earlier. But this is also kind of the popular approach people try to establish convergence in the literature. So the idea is basically the following. So let's look at this, define this minimal norm solution W bar. And this W bar is basically the weight, the initial point W0, right? Times, times this A, that is the coefficient we used before for the initializing your neural network, and the V, which is the representation of your value function in the RKHS. Right, so we define this W bar here, then you can immediately show that by definition, if you look at the gradient of V hat times W bar, then this will converge to the true value function as m goes to infinity. Okay, so if you write this down here, so you will basically get just nothing but 1 over m. So this gradient here, you have 1 over square root of m indicator function x transpose, and times these two terms. And this is kind of the reason why we use symmetric initialization, so this gradient times W0 will be just essentially 0, right? So this will give you just nothing but 1 over m, your feature vector times V, and because those Wi are IID Gaussian, so as m goes to infinity, this will converge to the neural tangent kernel, and that will converge to V of x, right? By definition. So this basically essentially means your V of x. So this basically means W bar is essentially, you can view this as the optimal solution if the optimal solution if your Vx is just a linear function, right? And if we define this, consider this Niao He function, which is just nothing but just a square distance between your estimator W and W bar. And you can show that there is a very nice drift analysis of this Niao He function. You can show that if you look at the difference between these two Niao He functions at the two consecutive iterates, there is actually a negative drift, which relates to kind of what we wanted to minimize, right? The distance between your value function and the true value function, plus some error terms. And those error terms depends on, say, for instance, how you choose your step size, alpha, and how many neurons you use to estimate your function, right? So this is basically kind of the key result that we base on. And this drift bound only holds true if t is smaller enough, right? If t is smaller than the stopping time, and we define the stopping time as the smallest iterate where your Wi will be far away from W0. So basically, as long as your number of iterations does not go to too large, or if your Wi does not drift too far away from W0, then you can establish such type of relationship. And then basically by telescoping this equation here, you will be able to show convergence of this this term here, right? By just telescoping, taking the sum from 0 to t, and with properly choosing m, right? Then you can actually control this distance here, which is kind of how what is the error you get with your estimator, right? So that is kind of the key idea. And in fact, this is kind of a very standard also in the analysis. Say, for instance, let's look again at this Wt plus 1. This is basically just the Wt plus alpha times gt, and gt is given by your temporal difference, which is delta t, times the gradient, right, of at w. And if you just take look at the Niao function and you just expand it, you will see that oftentimes you have this cross term, which is your semi-gradient gt times the difference of Wt minus w bar. And then you have this square term of your semi-gradient, which can often be controlled, right? This is bounded by some constant. So this will basically just of order alpha square. Like if you choose alpha small enough, then you will be able to control this term to be very small. So the important term is, of course, this intermediate, this cross term here. And for this cross term here, if you just plug in the definition, right? Again, this gt is just the temporal difference times the gradient, right? Times this is the inner product here. If you look at the first two terms, right? The gradient at w times w. Actually, this because of we're using the rectified linear unit. In fact, this is exactly just the value function at Wt, right? Because this is just the indicator function times w times x. So this is nothing but just the true value function at the Wt. Okay, and if you look at this w bar times its first term, as we mentioned earlier, if you use w0 instead of Wt, then this work essentially converts to the true value function, right? So basically let's just plug in those two terms, right? So this first term is coming from this first term, and we're going to add and subtract the value function, true value function. We're going to add and subtract this gradient, replacing Wt by w0, okay? And then this is the second term here in the previous step. So if we decompose it this way, and you then can immediately see like how this will work out, right? The first term here is kind of the standard TD learning analysis. And this is bounded because, and you can show that this temporal difference, because you are using this Bellman operator, this actually expectation corresponds to some contraction, right? That's why you get this 1 minus gamma times the square norm of the v hat and the v. Okay, that's kind of follows immediately from there. If you look at the second term here, what is it? Second term is basically measures, as we said earlier, if m goes to infinity, then this is going to converge to vx, right? So the second term basically characterizes how good your function approximation is to the neural tangent kernel, right? So that is controlled by this 1 over square root of m. And the last term is basically the difference is controlled by the difference between w0 and wt, right? It's like how your parameter deviates from the initial point. And as we said, if we consider our stopping time tau, so before the stopping time, this is always bounded by 1 over square root of m. So you can control all of these terms, and then you get the drift bound we discussed earlier, and then this leads to the final convergence, right? So this is kind of the high level. Actually, this is essentially the whole proof. Oh, this is not exactly the whole proof, right? So you still need to show that, of course, your stopping time tau is bounded, right? In the case, so we wanted to still show that like within the number of iterations t, right? So if you're running this algorithm for t number of iterations, indeed this deviation can be bounded. So that means T cannot be too large, right? In the case if we use maximum regularization, then of course this stopping time tau is just infinity, because every iteration you are enforcing that this bound holds true. But if we don't use any regularization, we want to show that indeed this stopping time tau is larger than the number of iterations you use, right? For a fixed amount of number of iterations, indeed, you can guarantee that your deviation of W is bounded. And this we can easily show by just using some standard results of martingale concentration and using again the drift analysis to try to bound the deviation. And I will not go into the details here. I'm just trying to keep track of the time here. Okay. So this is how we can actually show that the stopping time that everything actually holds with high probability that within this fixed number of iterations, indeed you can control this deviation of your network weight parameters. And that completes the proof here. So as an immediate extension, we can extend like so far our analysis heavily depends on this IID assumption on the samples. We can easily extend this to Markovian settings using these mixing time arguments. We can, and you see that also here we are using just linear, the rectified linear unit that we use only consider a linear function instead of W transpose X plus B. We're just using W transpose X, right? You can also extend this to the case where you have this addition of affine terms, and this only leads to more extended feature vector, and then a slightly extended like a neural tangent kernel function class, and a slightly different definition of V bar. Everything will follow similarly. And the analysis can be potentially also extended to smooth activation functions instead of just this ReLU activation function. There are a number of interesting open questions. First of all, so all of these analyses are based on this one hidden neural network, right? Just a two-layer neural network structure. Can we generalize this to like multiple layer neural networks or other neural network architectures, right? If you use new layers, does this imply that you can further reduce the overparameterization complexity, right? That's kind of typically what people think is true for deep learning. And also, if you use multiple layers, do we still can we still achieve global convergence, right? It's still a non-convex problem. It's even more non-convex than before. Can we still have any guarantee in the global convergence? And in fact, this can be, and in fact, I think all the analysis like neural tangent kernel can be potentially extended to multiple layer as well. And also another interesting question is this early stopping or this maximum regularization or L2 regularization really necessary here, right? Because in practice, people don't do regularization, right? They just run TD learning or run Q learning with neural function approximation without any projection, or they run the algorithms forever, right? They don't really do any early stopping, right? Is this really necessary? So far, our analysis shows these are quite essential in order to have reduced the overparameterization complexity. And also, does this result extend to deep Q learning algorithms, right? Instead of just the policy evaluation, if you want to find the optimal policy, if you want to apply Q learning algorithms instead, does this generalize to that? And also, like we know that with Q learning algorithms, if you use function approximation, it may not necessarily converge, right? Even if you are using linear function approximation, not even to mention like if you use neural networks. Then what are the principled ways can we design RL algorithms to integrate it with nonlinear function approximations that guarantees convergence? Right, other than using these Q learning or value-based methods. So that will come to what I will discuss next is a family of optimization-based RL algorithms that can be easily integrated with nonlinear function approximation, and you can easily get some convergence guarantees. Okay. So maybe I'll stop here and to see if there are any questions. It looks like we're all good.
I think it's crystal clear.
Okay, that's good to know because I was worried that neural network stuff will confuse people. Okay, good to know that. So all right, let's move on then. So in the remaining time, I wanted to talk about other potential algorithms that we can more easily integrate with nonlinear function approximation. As you can see that even here with two-layer neural network, for these value-based algorithms like TD learning, Q learning, the analysis is already very complicated and very kind of hard to analyze. And so it would be interesting to see whether we can go beyond these value-based methods and derive more easier ways to integrate nonlinear function approximation. And this kind of what I would summarize as optimization-based RL algorithms. Many people don't agree with me because they think, okay, RL by itself is an optimization problem, and it's like solving it's trying to maximize the reward to get optimal policy. But you'll see that how this is different from kind of the value-based methods we discussed earlier about Q learning and TD learning. As I said, those algorithms, while they can be interpreted more or less for solving some optimization problem, but they're not really computing the actual gradient, right? It's some semi-gradient that it's not really capturing the true gradient. Here, by optimization-based reinforcement learning algorithms, I'm really referring to problems where you pose an explicit optimization, static optimization problem, and you try to solve it based on gradient methods or first-order methods. So the first category, which I call it Bellman residual minimization methods, that was trying to minimize the Bellman errors. And this include many interesting algorithms like the gradient TD learning algorithms and something that I will discuss later called the speed algorithms that we proposed a few years ago. And then there was the other family of algorithms that are based on the linear programming reformulation of Markov decision processes. And there are lots of interesting algorithms like primal dual algorithms and mirror descent algorithms for solving this to find optimal policies, and those algorithms can be easily integrated with nonlinear function approximation. And there is also a third class of algorithms called policy gradient method that directly tries to maximize your non-term reward by computing the gradient over a class of policies, and you're directly trying to compute the gradient with respect to the policies directly, right? So those are fundamentally different from the value-based approaches we see before. And we'll discuss each of them, at least one example for each of them. And I would say that there are many advantages of considering this type of optimization-based RL algorithms. First of all, because they're also, like control theory, we do have also very rich literature and theory algorithms for gradient-based methods for optimization, both convex optimization or non-convex optimization, which many of you are probably more familiar with. Also, there is much easier for us to exploit off-policy data. Unlike the co-learning and TD learning algorithms, we know that they might potentially diverge. with off-policy data, but with these optimization-based approaches, you will see that it's much easier to integrate with off-policy data, and that's what Bo will talk about this afternoon more extensively. And it's much easier to adapt it to function approximation. And lastly, I should also mention, I think they're much more adaptive and extensible, because all of these optimization frameworks can be easily generalized to other settings. Say, for instance, if you have safety considerations, you just add a bunch of constraints to your optimization problem. If you are dealing with multi-agent reinforcement learning, then you just pose this as distributed optimization problem, right? So it's very easy to adjust to different other more complicated scenarios. And similar, unlike before, there is also a common recipe here, right, to derive or to analyze optimization-based reinforcement learning algorithms. Oftentimes, we just treat this as an optimization problem. Either you are minimizing some loss function, or you are solving a min-max, a two-player zero-sum game problem that you want to minimize over X, maximize over Y. And then you can deploy many of the existing first order methods like gradient descent, stochastic gradient descent, mirror descent, variance reduced gradient methods, primordial methods, Frank-Wolf algorithms, like all kinds of first order algorithms you can potentially be applied to solve those problems. I'm just giving you a couple of examples, right? Say, for instance, people have been using these primordial algorithms for a policy gradient, policy evaluation, and variance reduced methods also for policy evaluation. And also there are lots of first order methods for policy optimization as well. And I would say you can easily come up or show asymptotic convergence of these gradient-based methods based on the existing optimization theory. You can also use a lot of these techniques like acceleration, variance reduction to get better performance and improved bounds, right? So those are kind of also very neat in comparing to the more controlled theoretical analysis. So first of all, I'm going to give you an example of this residual, Bellman residual minimization approach, right? So if you look at this, again, coming back to this Bellman optimality equation, we want to find the optimal value function V star. So in all of the Q-learning algorithms, we're basically iteratively solving this, right? And as we mentioned earlier, there was this difficulty mostly coming from this max operator, because this is highly non-smooth and it often causes instability or maximization bias. Especially if you are using function approximations, okay? And here I'm going to just rewrite our Bellman optimality equation by using this policy pi, right? So instead of taking the maximum over a finite set, I'm going to take the maximum over the simplex set over a distribution, right? So these two are equivalent to each other. And normally when you encounter something like a simplex set or like some distribution, probability distribution, you think about, okay, we should be using entropy, right? Here, let's just add this entropy regularization into the Bellman equation. Okay, so here I'm just considering this coefficient lambda, which is a regularization coefficient, times this entropy H defined over your policy pi. Okay. And I'm going to call this the smooth Bellman optimality equation, or if you rewrite this, if you plug in the definition of pi and compute the max, you'll see this is nothing but just a softmax operator. Okay, so you have this very clean form, a smooth operator, log sum exponential form. Okay, and this lambda here basically controls how close your value function is to the true value function, optimal value function. I'm going to denote this as V lambda as the fixed point to this softmax operator here. Right, so you can show that this softmax Bellman operator is also a gamma contraction, like the original Bellman operator. And you can show that the difference between this this new or this approximate value function is not too far away from the true optimal value function. The difference is controlled by this lambda, right? Smaller lambda you use, then the bias is small, but this will be less smooth. And if lambda goes to infinity, then this reduces to the original Bellman optimality equation. And you can also have a even simpler form of this Bellman equation by just considering both value function and the policy pi, right? So you can show that this optimal value function v lambda and the optimal policy, corresponding optimal policy pi lambda satisfies this Bellman equation below, right? The difference from the optimal optimality Bellman optimality equation is that you have this actual logarithmic term here, and you don't have a max operator anymore. Okay, so intuitively, if you want to solve this Bellman equation, the idea would be, let's just try to minimize the mean squared Bellman error, right? Just like what we did for TD learning as well. So we try to minimize the mean squared Bellman error over both value function v and pi. So notice that this problem by default is not, it's convex in v, right? Because this is a square loss with linear in v inside, but it's not necessarily convex in pi, okay? And if you solve this directly, you will encounter this so-called double sampling issue. Like if you just want to compute the true gradient, as we mentioned before, if you want to compute the true gradient, you have to compute, you need to compute the gradient of this part, right? And you need to estimate this whole thing here. So you need at least 2 independent samples from S prime in order to construct an unbiased estimator of your gradient. And in practice, oftentimes, you only observe one successor state for any given state action pair, right? You don't really have 2 samples. So you cannot really just apply, say, stochastic gradient descent to solve this type of problem. So what we propose instead is, let's just consider a reformulation of this problem by using the Finchl duality of this square loss function. So if you apply like a Finchl duality of this square loss function, I can kind of extract this like inside term here outside, right? So this will then gives you rise to this following min-max optimization problem. And the interesting thing with this min-max reformulation is that now you don't have to deal with this conditional expectation anymore. You only need to deal with this joint distribution over state, action, and S prime, those triplet here. And this you can easily sample, right? You can get one sample of this and you will be able to then estimate this objective. And you will be able to apply, say, for instance, stochastic gradient descent directly to solve this min-max formulation. So the caveat here, though, is that this dual variable rho here is not a scalar vector anymore, right? This rho is going to be a function of your state action pair, right? Because if you look at this objective here, for any state and action realization, there will be a corresponding dual variable, right? So hence here, you do have a function of dual variables. And you do need to also incorporate some sort of parameterization to make this problem more tractable, rather than just dealing with a infinite dimensional continuous space here. So that is essentially what we propose, right? We can then basically parameterize your value function using some neural networks. We can parameterize pi using neural networks. We can parameterize this dual function rho with some neural networks. And then this will give you some non-convex minimax optimization. And then you can just directly use stochastic gradient descent to solve it. So the algorithm sketch that we propose is basically to say that, so if you look at this problem here, we're going to just say wrong, next for any fixed v and pi, we are going to solve this max sub problem here to find the best rho. And then we're going to use that rho to compute what are the gradient for v and pi, and then we're going to update v and pi recursively. So that is the algorithm we propose, and we're calling this the speed algorithm, which refers to the smooth-Bellman error minimization algorithm. And you can, as I said, you can easily incorporate nonlinear function approximation here. You can also easily incorporate many of the other techniques people proposed in deep learning, like deep reinforcement learning, like experience replay, and so on. So that's what, and also you can easily use behavior policies to offline data of policy data to generate samples and to construct gradient estimators. So that's kind of a more comprehensive or slightly more complicated algorithms we propose. And we'll be able to also derive some sort of asymptotic, like convergence guarantees for this algorithm. So particularly, say for instance, so this is some experiments we did a while ago, and we compared the approach to various other state-of-the-art policy optimization algorithms like trust regime policy optimization TRPO, or this DDPG algorithm like deterministic deep policy gradient methods. And we've shown that our algorithm actually has somehow my video is not showing up here. Sorry. Okay, so so there was only one video is working, the middle one. Okay, so you can see that. So you can see that actually it initially it actually okay, it's kind of slow here, but you can show that only after within like less than 100 iterations it was able to achieve a relatively good policy there, right? And kind of that is like just one example of this Bellman residual minimization approaches. So another kind of different approach was to using this linear programming reformulations for Markov decision processes. And from even any textbook on reinforcement learning, you will be able to see this type of primal and dual linear programs for MDPs. Particularly, like say, for instance, the primal linear program is given as the following, right? And so you have a linear objective. So mu0 is your initial distribution. And here, these constraints basically corresponds to the Bellman equations, as you can see. You can write down the dual formulation of this LP, or this actually can be also easily derived based on this definition of this state action visitation or occupancy measure rho, and this gives you the dual LP. And the nice thing with the dual LP is that this occupancy measure rho SA, actually, if you solve this, if you get the optimal dual solution, you can use it to directly construct what is the optimal policy, right? So in practice, oftentimes people just direct, for small Markov decision problems, people just directly just solve this dual LP, and that will give you the optimal policy pi star. For large scale problems, of course, you cannot directly solve this primal problem or the dual problem, right? So by Lagrangian duality, we can also write down the saddle point formulation of the primal or dual problems, right? So all of these three problems are essentially equivalent. So the nice thing with the saddle point formulation is that you don't have any constraints, right? You just have this objective here, which you can actually easily draw some. You can actually use the samples from the op policies to construct unbiased estimators for this objective or this cost function here. So building on these LP formulations, there are actually many like algorithms people proposed. Say, for instance, you can use these primal dual algorithms to solve this bilinear saddle point problem, or you can use, say, a more general version of gradient descent, like mirror descent, to solve the saddle point problem as well. And in the recent result, so the way how you do with update for, say, the dual variable row is, instead of using the gradient descent, which typically you are going to use a square norm distance here, you are going to replace that by, say, for instance, a KL divergence between row and the previous iterated row T, right? So this is called a mirror descent step, or this actually oftentimes gives you multiplicative updates for your vectors row. So recently, I think there were results showing that if you use this type of KL divergence in your update, or using this mirror descent type of algorithms, you were able to achieve much better complexity in terms of the dependence on state and actions. So you can also solve the dual problems directly, right? If you solve the dual problems directly, you can use, say, for instance, also you can use just mirror descent to solve the dual. This will be then equivalent to using proximal point algorithm or so-called augmented Lagrangian method. All of those are sort of equivalent, and this reduces to some of the existing studied algorithms in the literature. The idea is also similar, right? You're going to just use some, say, for instance, some KL divergence to regularize your objective. So, and the difference between these two approaches here is that here you oftentimes we use a fixed regularization, whereas in mirror descent we use a much smaller step size, and where, yeah, I think those are kind of some of the differences there. And you can also easily combine all of these approaches with linear or nonlinear function approximations, rather than just dealing with the tabular setting, right? There are lots of results that coming out. But the caveat here, though, is that when you integrate with nonlinear function approximation, then you will immediately lose strong duality. So the dual is not necessarily going to be giving you the exact solution for the primal problem. And then because you're using nonlinear function approximation, the landscape of the solutions are much more complicated, right? There will be many more stationary points or saddle points rather than just the global optimal solutions, right? And it's slightly harder to characterize the approximation errors because here you are basically relaxing off the constraints with function approximations rather than, so this is slightly different also with the value-based methods. Nonetheless, I would say there are lots of recent progresses in solving non-convex, non-concave min-max problems. And we now have a slightly better understanding of what are probably convergent algorithms for solving such non-convex problems, and what are the landscape of them. So those new advances in the optimization side could be potentially useful to generate new insights for reinforcement learning. So lastly, I want to also briefly touch base on the third class of optimization-based methods, which are called policy gradient methods. And policy gradient methods consider directly the original objective instead of these intermediate objectives that are derived from Bellman equations. They're just going to just consider maximizing the value functions over a class of policies pi. And assuming those policies pi are a parameterized class of functions. Say, for instance, in the tabular setting, we can use direct parameterization. So basically, for any state action pair, you can use one parameter theta to represent it. So your theta basically is going to be in some high dimensional simplex. Or you can also use this softmax parameterization by just taking this softmax form, right? So the difference between these two is that the number, you see that the number of parameters is the same with the direct parameterization and softmax parameterization. The difference is that for the softmax parameterization, there is no constraint on theta, right? Whereas in the direct parameterization, you do have to constrain theta in some simplex. So if you directly apply this direct parameterization, oftentimes you have to do projection. You have to project on the simplex, which is slightly more expensive. You can also use function approximations. Say, for instance, you can instead of using this, you can also use something similar to softmax parameterization, but now you're going to consider, say, for instance, this linear function approximation. So this is oftentimes called the log linear policy. You can also use neural networks inside your softmax parameterization, and this is oftentimes called a neural policy. Right, so the idea is basically once you represent your policies with this parameter theta, and then you just directly run gradient descent over the theta, right? So you compute the gradient with respect to theta, and then you just do gradient ascent here because you try to maximize the value function. Okay, so I have not told you how to compute exactly the policy gradient, right? How you estimate the policy gradient or construct unbiased estimator for it. There are lots of kind of approaches that you can do that. And it's kind of not too hard to see that this problem is fundamentally non-convex. So if you apply this type of policy gradient method, it may or may not converge to the global optimal solution or global optimally policy, right? So one thing that was heavily used in practice, as I mentioned in the very beginning, is the entropy regularization. As you see also in the other two approaches, like the Bellman residual minimization or the linear programming cases, we also use the entropy regularization extensively. Here, for entropy regularized policy gradient, oftentimes we just also directly add this entropy regularization into your objective, right? And then I'm going to call this V lambda pi. This is a slightly different objective, and you can also control the difference between this and the original objective by this regularization parameter lambda. And you can show that you can actually also compute the gradient with respect to this entropy regularized objective. And the gradient will be given by this term here, which depends on kind of the state action value function Q at the current policy pi theta. And also it depends on this state visitation distribution here. So oftentimes in many of the literatures, people can come up with all kinds of ways to estimate or sample from this state visitation distribution, and then to estimate these Q functions. And then you'll be able to get unbiased or potentially biased estimators for this policy gradient. And then you just do run again policy gradient on this new objective. And again, although you add this regularization parameter here, this objective is still non-convex, right? And for entropy regularized the problems, you can, as I said, you can directly use the policy gradient methods to, so instead of the original gradient here, you just take the gradient on the regularized objective. So there is also the family of natural policy gradient methods where you use this Fisher information matrix to do a preconditioning of your gradient. Or you can also view this as just applying natural gradient descent to this regularized problem. And this Fisher information matrix is given by this following definition here. And one can also show that this natural policy gradient, which is popularly used, is indeed nothing but just the soft policy iteration. This is also closely related to soft Q-learning algorithms as well. And it can also be viewed as a special case of a mere descent algorithm. which I will not go into details here. I think Bo will probably discuss more in details in the afternoon. And as I said, all of these problems are inherently non-convex, but there are many very interesting recent breakthroughs on understanding the convergence of policy gradient and natural policy gradient. And many of these results shows very intriguing and also exciting results about global convergence. And particularly, there were a recent line of work that shows that if you look at just the tabular setting, right, and if you do this softmax parameterization, and in fact, if you just do this policy gradient or natural policy gradient, they will converge to the global optimal solution, although your problem is non-convex in nature. And they show that for policy gradient, you can actually achieve this 1/t convergence rate. And this can be improved to a linear convergence rate if you use entropy regularization. Okay. And similar results can be obtained in the function approximation settings. Particularly, it was shown that for natural policy gradient, if you use log linear policies, then you will get this 1/t convergence rate. If you use neural policies, you can also get this 1/t convergence rate, but you will need very massive overparameterization, say something like a t to the power of 6. And all of these are showing basically sublinear convergence when you use functional approximation, unlike the linear convergence case, unlike the tabular setting. So there are a number of interesting open questions, like say, for instance, what are the sample complexities or the convergence rate should be if we don't have the exact gradient, if we can only estimate the gradient through some samples. Right, so there are some recent work on this, and more details will be discussed in the afternoon. And another question is, naturally, does entropy regularization help in the functional approximation setting? In the tabular setting, you get a faster boost in the convergence, right? You can boost the convergence from sublinear to linear. What about functional approximation case? So recently we had some ongoing work that shows indeed you can also get linear convergence for policy gradient if you use even in the functional approximation setting. And lastly, also, can we really improve this overparameterization bound that was in the existing literature, which is like t to the power of 6, right? Which seems to be overly pessimistic somehow. And some of the analysis we did earlier for the Wtd learning can be potentially useful here to get better overparameterization complexity. And I was going too fast. Okay, here. So I wanted to basically, lastly, want to briefly discuss this entropy regularization, right? What's the role of this entropy regularization? I think we have seen this used in many occasions, right? In the value-based methods, like soft Q learning algorithm, in Bellman residual minimization problems, like in our speed algorithms that we use this to smooth out the max operator as well. And in the linear programming-based methods, we use this extensively to optimize over the simplex set or the probability distribution set to get a better convergence guarantees. And in policy gradient methods, this was also extensively used to achieve faster convergence. So there are many other algorithms that also used or explored entropy regularization, but they are somewhat different in nature from what we have discussed here. And the question here is really that we have seen many different evidences of many different aspects of this entropy regularization, right? In some cases, this was basically used to avoid doing projection on the simplex. It helps you to stabilize training. It achieves better convergence. The folklore theory says that entropy regularization helps you with exploration. And so I would say there is a bit of each of those in different settings, and I would say this is definitely very powerful or useful technique for this type of optimization-based reinforcement learning algorithm. So lastly, I think I should really stop here, and I want to summarize that I discussed the two parts, right, in this talk. The first part is about the asymptotics of reinforcement learning, and through this close synthesis between control theory and reinforcement learning. Second part is more about reinforcement learning with nonlinear function approximation, different algorithms, how can we get some theoretical guarantees when nonlinear function approximation are used. And the key message here, as you can see, that regularization is super important, both in terms of the optimization aspects and also in terms of the generalization aspects of reinforcement learning. And with that, I guess I will conclude the lecture now, and happy to take any questions you might have. And I should also really thank all of the collaborators and students in the lab for this for all of the results we presented today. And this afternoon, Bo will be talking more about how to combine reinforcement learning with offline data and online exploration. Okay.
So there is still a couple of minutes to take a couple of questions, if there are questions from the audience. Otherwise, I do have a quick question for you, Niao.
Sure,
so
yeah.
Thanks. So you briefly discussed about primal dual methods, and there have been recently many works on primal dual methods for reinforcement learning, with also a lot of solid theory. But as you also mentioned, these methods rely on duality theory and strong duality, which implies then convexity. So so far, they are kind of limited to the linear architecture case, right?
Mm-hmm.
Do you believe this to be a major limitation of this class of methods, or do you believe that there are ways to extend those with more advanced theory tools to also handle the class of nonlinear function approximators? Because at the end, it's there that somehow we would like also to go, because of the all empirical evidence of the success stories of this reinforcement learning agent when used in combination with these powerful parametric approximations.
Right. I think that's a very good question indeed. And you see a lot of numerical evidence, not only in reinforcement learning settings, but also in, say, in other machine learning applications like training GAMs, generative adversarial machine learning, right? So all of those, actually, you have to deal with these min-max problems using primal dual methods over like massive amounts of like large neural networks. And just surprisingly, for many of these applications, people do observe like global convergence, or oftentimes they are able to actually recover the optimal solutions, right? So I think first of all, it's still a very viable approach, although theoretically speaking, you might be losing the duality, strong duality there. But I think it will be interesting here to consider, like, when would you be able to establish strong duality, right? Like maybe with enough overparameterization. Say, for instance, something similar as what I discussed for the neural Wtd learning case. If you use two-layer neural networks for the primal and for the dual, and they are approximately going to be just a bilinear problem, which has some hidden convexity there, right? So that might be able to alleviate the issue with the lack of strong duality, or maybe you can show something there. So I think those are in general very interesting open questions, and they would be very perfectly suited for a PhD project, right?
Yeah. Many thanks.
So maybe I can also ask a question. So I have a question regarding the LP approach that you presented. So I do understand that it can be used to model the underlying MDP problem, right? And then it gives rise to different algorithms that have been presented using the LP formulation as a kind of starting point. However, also somehow it seems that the LP approach is quite fundamentally different in the sense that it's kind of a one-shot problem, right? So you don't solve something iteratively, you just have a, like a static optimization problem, you solve it, you get your optimal policy. So now what's your view on that kind of modeling framework? Like, is that, so when would you consider this as a useful kind of problem modeling? Because it seems like, so sometimes, like doing something iteratively, like the value iteration, policy iteration seems much more powerful instead of, like putting everything into one single optimization problem and solving that in one shot.
Right. So, so I think that's a very good question, first of all, and I would say, even in the tabular setting, in the very classical theory, we know that solving this LP formulation actually is much better than the value iteration or policy iteration. So first of all, you can show that because with a linear programming formulation, this is actually a tractable convex program, right? People can actually show that you get a strongly polynomial convergence, polynomial complexity for solving this LP. Whereas if you do value iteration, you get linear convergence, but those are not necessarily strongly polynomial algorithms, right? So solving LP should be much faster than the value iteration, policy iteration, if you know the underlying dynamics very well. And that is actually what people normally use in practice to solve small scale MDPs, right? The interesting question is then, like, is this amenable for function approximations? There are also lots of, I think, papers on approximate dynamic programming in the classical literature, right? I think it's not any worse than all the value-based methods like value iteration or policy iteration. And I think using this optimization or LP formulation, it really is it's kind of, because I think both of them are boils down to this Bellman equation, right? Both of them are derived from Bellman equations. So that's also is a very interesting question, is like, there are so many different ways of formulating Markov decision process, so many ways of formulating an optimization and objective to get the optimal solution. Then which one is better, right? What should be the right objective? What should be the right loss function? What should be the right optimization problem to start with? I think that's not very clear at the moment. What should be the best thing to do? I think there was also a recent work that I think I mentioned it in one of the slides that considered this logistic Q-learning, and they were basically proposing different loss functions, different objectives, rather than the mean squared Bellman error. They were using some logistic-based Bellman errors. So I think there is a large room of research, open questions there. Yeah.
Cool. Thank you so much.
Are there any other questions from the audience? Otherwise, well, we'd like to really thank you a lot, Niao, for the really nice and interesting lecture that you gave, and also for having endured all these hours of lecturing. Many thanks. And for further discussions, we will use the Slack channel. So we have a dedicated channel for Niao and all our lectures. And then we will continue this afternoon at 2 with Ode and his lectures on offline